now the discussion will be about DRST formalism. And so essentially, it's the following observation that this space where this Fourier-Popov function belongs to, so this is the function. In Yang-Mills theory, it's also called the action with ghost fields. So these are ghost fermions. So it's a function on this supermanifold, and it's an element of this vector space. So first observation is that there is this odd operator acting on this supervector space with the property that its square is 0, so it's a differential. It annihilates this function, and also this function can be represented as f, the kind of initial function that we started with, plus q of some element of this vector space. So it's a cochain complex, and the Fourier-Popov action is a cochain, and the corresponding homology class is the initial function f. So now the interpretation of this complex. So here is the standard complex in representation theory in the theory of the algebras, the Chevalier complex with coefficients in this representation of G. And then by mistake I was calling this complex the Ram complex, but it's not the Ram complex. It's easy to remark that it's a Kashut complex, and the cohomologies of this complex is exactly this vector space. And so with all the assumptions about the action of G on M, the complex is acyclic, so only 0 cohomologies survive. So let me call this space H. Well, H is, say, V. So H0 V is equal to C infinity and G.
Did you figure out the dual? I mean, we sort of have only one G star over there.
No. Instead, I was busy correcting the first lecture, so I didn't have time to correct the duals. But I did correct the first lecture, so after we finish with DRST, we will derive the Fourier-Popov theory. So, okay, so that's part of the story. So, good news is that there is some cohomology structure behind these fermions. And even better news is that this cohomology structure is a composition of two standard differentials which are known in algebra for a long time. And DRST just probably didn't know it. They certainly invented this construction in the context of this theory. Okay, so now how to use this, and what are the conclusions of this construction? So certainly we see that really the space that is most relevant to the integral in question, and remember that the whole discussion is about the integral over m e to the I f of x over h dx. dx is g invariant, f is g invariant, g acts on m, so this is equal to g times the integral m over g e to the I f over h dx. So really the most important object is this one. It's the integral over m mod g of this function. But now you can see that this Fourier-Popov theory, what it does, it represents this integral that we really care about. In terms of the integral over this supermanifold of e to the f, where f is this thing, but this thing is an element whose is a cocycle whose cohomology class is exactly the function that we want to integrate over this space. So it suggests the following general algebraic observation, which in some sense explains the algebraic nature of Faddeev-Popov theory. So let me just recall some general linear algebra. So suppose we have a super vector space D, C, and the differential acting on C. D squared is 0. So suppose we have another vector space and the differential on this vector space. So suppose we have a non-degenerate pairing between them such that d star L A is equal to -1 to the L bar, assuming that L is homogeneous, L dA. So here we have the cohomologies of C, which is the kernel D over the image D, and same here. So small linear algebra lemma is that if L and A are cocycles, so L is in C, A is in D. So one is cocycle with respect to D, the other is the cocycle with respect to D bar. Then if you take the pairing between them, it will be equal to the pairing between the cohomology classes, and so we have a pairing between C and D. It induces the pairing between H, C and HT.
The lemma is that the pairing only depends on the homology class.
Exactly. Yes. So basically that's the statement. So it's a linear algebra exercise, but that's a very nice fact. It says that suppose we want to compute this pairing, but it's very complicated. So what may happen is that you may find some so suppose that initially you don't know that these vector spaces are cohomology classes of some complexes, just some complicated vector spaces. You want to find a pairing between the cohomology classes. So then suppose that you constructed this resolution, so suppose that you constructed cochain complexes C and D, whose cohomology classes are HC and HT. So then, if you want to compute this pairing, you can compute the pairing between representatives. And this will give you the alternative computation of such pairing. So, and this is exactly what happens in this Faddeev-Popov business. So this is the It's a very intuitive explanation. So now, what we want to do is we want to compute the integral over mg e to the I f over h dx. So integration over the space of orbits. So in this case, we can think of this as a pairing between functions and measures. So the statement is that this is equal to the integral over this space, even order, e to the I f p dx d lambda dc bar dc. So this is the pairing between representatives of whatever. So I don't want to go into this analogy too much because so I just want to leave it at this semi-intuitive level, but you can see that sort of it opens up a lot of algebraical possibilities. It's simply not necessary to use, for example, this particular resolution for these cohomologies. One can imagine that maybe there is some other cochain complex which is even more convenient, which you can use to compute this integral, basically using this length. And this is the first step towards this, it's called Batalin-Vilkovisky quantization. So the only problem with the Batalin-Vilkovisky quantization is when the distribution is non-integrable, there are no invariant functions. It's not quite clear what it computes. There is a machinery, but it's not clear what it actually computes. So when the distribution is integrable, that dissipation is very parallel to this one, and essentially there is this kind of almost canonical resolution, but it's not in terms of the Chevalier complex for the algebra action, but it's like the action for it's the analog of this for integrable distributions. Okay, so this is the essence of BRST observation, that this fermionic integral is nothing but the computation of this pairing using some kind of cohomology theory.
Yeah, you mentioned Batalin-Vilkovisky. So this is when you don't have a group action, or what was the situation?
Pardon?
I mean, this Batalin-Vilkovisky, this is when you don't have a group action.
Yes, but
So I mean, next step would be if you had a fibration. But,
even next step after
or
this.
fiber bundle, yeah. And then even you can ask for distributions even.
Yeah.
That's what I was discussing at the end of the last
Group
lecture.
action, vibration, integral foliation,
Yeah.
just distribution. That's
Right.
Okay. Yeah.
This Q is actually F is Q closed, isn't it? So
Yes, F is Q closed, but
maybe
because,
I
but
don't
also
understand why if Q satisfies kind of Leibniz rule to allow.
it's a first order differential operator, so it also annihilates the exponent.
Okay.
Yes.
This is headings.
How Q acts on the dual on the measures? It's just an exercise number 7, or
Just let's leave it, because I mean it's nice to discuss it in this context, but it's part of a bigger discussion that where VV should be present. Otherwise, it just will end immediately after this explanation. But so let's just. So I hope it's clear that what is the idea of BRST. But then I wasn't planning to discuss the details of this. So it is a certain conceptual, algebraically conceptual explanation of why we have fermionic ghosts in this approach.
So one needs to check that dx is closed under Q-BRST dual.
Yeah. But I will leave this as you just suggested as a homework exercise. So to check that the measure is closed with respect to the dual differential. But that's essentially the G invariance of dx from this focusing approach. Okay, so any more questions about BRST? So then I will return to the beginning of the morning lecture, and I will actually derive this identity again. Not again, but I'll actually derive it. So what we want to prove is that integral over m f of x dx is equal to g integral over m e to the I f of x over h delta x delta phi x dx. So where phi x is just the collection of these constraints. Phi x delta x is the determinant of LAB x, where LAB is just EA dB x. So let's just break this. So that's the statement. Proof. Let's break it into 3 steps. So first, let del x be the function determined by this equation. Well, obviously my mistake in the morning was that I forgot about phi. So this delta depends on phi, and that's the so this is the distribution supported. So fix x on m. So then this is our point somewhere. It lies on certain g orbit. This is x. This is our constraint surface cross-section S phi. And at some point, at one point, the g orbit through x intersects S phi. And just for the future use, let's denote this point as g0 x, where g0 is some function of x. So then we can compute this this del x, and this will be step 2. But first, let's just insert this 1 into this integral. So if this is I is equal to integral over m dx dg dx. Now, so any group has the right invariant measure, so let's use this measure in order to define delta.
I just have a question about how you think about this equation here. So, why is delta of x constant equal to 1?
What?
Why, I mean, so how do I think about this equation here? So delta x times, and there's an integration of this delta function.
Yeah.
Because it seems that this delta function gives a beep right at G naught.
At S.
At S,
At
which
the
is
beep
G
at
naught.
S.
G naught is defined to be that, so it gives a
G naught
beep.
x.
So it gives one beep there, boop, and then sort of, I imagine when I integrate that up, it gives me a 1.
No, let's compute it. It gives the Jacobian. So let's compute it, just so that there will be no ambiguities. So dg, you're absolutely right. It's so the contribution comes from the infinitesimal neighborhood of the point g0 when you integrate with this. So I'll write it like this. It's the integral over t g0x, and then let's see how. So this is the t are very small, so they are in the infinitesimal neighborhood of the identity. So this exponentiates the coordinates in the infinitesimal neighborhood of the identity. So this is where the orbit intersects the cross section, and so this is equal to phi g0x, which is 0. Let's say b plus sum over a ta ea phi b g0x plus higher order terms. So when we're computing this integral, it becomes sum over a ta ea phi b g0x dt, which is exactly the determinant of L g0x inverse. So this is the result. This is the delta.
Right, so when we think of this in the distributional sense,
Yeah.
then sort of
Yeah, I mean,
it transforms according to the first order.
but I mean, it's almost easier to think of it as some function which is concentrated very close to.
That's fine because because it's a distribution that's supported right at the zero, right? When we go to the tensor.
Yeah, so you have a function supported very close to zero.
Absolutely. And we integrate it against this, and then somehow it's just the coordinate transformations of the linear part that tells you that the determinant comes out as the factor.
But I mean, there are no deep facts about distributions here.
No, not at all. I just mean a rigorous sort of interpretation of it. Right? Because it has to be done in terms of distribution to really get the determinant out.
Well, no, I mean, if you want to do it in terms of distribution, you should smooth it. So you should make it.
Well, you evaluate this on the test function.
Yeah, against this function,
Right.
but that's essentially what it is.
Because I mean, you know, this is a function that's 1 at 0, at the zeros of this function, and it's 0 elsewhere, right?
Well, it's infinity.
So I'm
Infinity, right.
I'm using this fact that if you have a distribution, if you integrate it against some test function dx, this is equal to the determinant of L inverse h0 over Rn.
Yeah, where L is some linear transformation.
Yeah.
Yeah. Yeah.
Which, yeah.
Right. That's good. That's what I'm
Okay, so this is delta. But now, an important property of delta is that it's G-invariant. It's clear. So we will take the definition of delta. It's delta phi gx dg. This is equal to, well, dg is equal to dgh, so we will change the variables to g prime, which is gh. So you see gh is how the word ghost starts.
Wait. So this here are determinant inverse.
But yes, so
but
delta,
on that blackboard it says determinant. This is
yes, but you see delta times this should be equal to 1.
Yeah.
Oh, sorry. Yeah. Okay. Very good.
So this is equal to delta hx integral over g delta phi gx dg, and this is equal to delta hx del x. So from here, no, okay. Delta x, but this was 1. So delta hx is equal to delta x.
And just a question about the B's. So there's a phi over there. There's a phi, phi.
Upper super B.
Yeah, a line above. I have delta phi of gx. So, am I summing? Or these are just the coordinates, I suppose, right? So phi, B runs from 1 to whatever it is.
Yes,
It's delta in that
yes.
space, right?
B is 1 to n. Yes,
Yeah.
it's a product of delta functions.
Right, exactly.
Product of the usual.
Yeah.
Okay. So then we can move from this line, and now we change the order of integration. So it's the integral over g, integral over m, e to the f of x over h, delta x, delta phi of gx, dx, dg. But now, here I can change the variables. I can denote gx by y, and then f of g inverse y is equal to f of y, delta of g inverse y is equal to delta y, and this measure is also invariant. So that means that the integration over g becomes the volume of g, volume with respect to the right invariant measure which exists on any Lie group, and then integral over m, the exponent I f of x over h, delta x, delta phi x, dx. So we've got this formula, which is almost what we want. Remember that we want to have the formula where delta is the determinant. Oh. Okay, so maybe I should write it. This is what we want. But delta is not the determinant yet, but that's very easy to fix. So let's just write again what we got. We got the integral over m, e to the I f of x over h, the determinant of L g0 acting on x, delta px dx. But now you see that the integration is supported on the slice, on the cross section. And for the points on the cross section, g0 is equal to 1. And from here we conclude that this is our formula. So this is what I was supposed to do in the morning.
When you change this order of integration, is that, I mean, sometimes this can be dangerous, but I say this is one of the cases where it isn't a very big step.
Yes, it can be dangerous when one integration, when the integrals converge non-uniformly.
Yes.
But here everything is compact, nothing is
And
singular except for the delta distribution.
Yeah, right, yeah. So, as you say, that is not serious.
Yes, this is not the case.
Okay, good.
It's
Yeah. I trust if you say that this is one of the simple cases.
Thank you. You shouldn't be very trustful, but
I mean, again, it's something. Remember, we are localizing it at a critical point or critical orbit.
yeah,
We take a compact neighborhood of that, and we do everything against test functions that have sort of a compact support inside there.
I don't see any obvious dangers. It's just I know that you have to be careful.
Right.
So that's why I'm asking.
yeah.
So that's the reason why.
Okay, so then this somehow closes the chapter on finite dimensional version of Fadeev-Popov and BRST. So we sorted out the asymptotical expansions of oscillating integrals, and we sorted out these expansions in two cases. First, what we did yesterday is when f has isolated critical points. So in all directions at this critical point, the function looks like a paraboloid, well, something like this. So it's in every direction it's a parabola. And then f has isolated critical orbits. So in this case, f is constant along the orbits. That's the way how it degenerates. But across the orbits, it's non-degenerate. So for example, the cases when it's x squared in one direction and x cubed in the other direction, important cases for many places in analysis, this is not what to do here. Okay, so in some sense, these are the two cases that are really relevant to quantum theory. So these are the two cases where this finite dimensional intuition will be generalized to the infinite dimensional set.
I mean, one could really say that the case you crossed out 3 is actually relevant for Chern-Simons theory.
No, I don't think so. Because if it would be relevant, then the expansion in K would have different exponents.
I'm sorry, it's 4, namely where the critical orbits are not isolated.
Yeah.
That's relevant for.
When there's something like this.
Yeah, there's a family of orbits that are critical, right?
Yeah. But still,
really
the
what
function
I'm
really
sorry.
is constant along these directions.
Right.
So in each direction it's either constant or non-degenerate.
Yeah. and hopefully transversely non-degenerate, because that's
Yeah.
what you're sort of trying to avoid.
Exactly.
But,
Okay, so then let's move to the real. Let's start the real action. Let's move from finite dimensional case to the infinite dimensional case. So what is the simplest? So now first I will discuss non-gauge theories, just infinite dimensional integrals in quote-unquote marks. And then next week we will focus really on gauge theories. So now first non-trivial example of a non-zero dimensional. So this is like a zero-dimensional quantum field theory. One-dimensional quantum field theory is quantum mechanics. Just as classical mechanics is a one-dimensional classical field theory, so quantum mechanics can be thought as one-dimensional quantum field theory. So now let's look at the, let's go quickly through the Schrödinger picture of quantum mechanics and the semi-classical limit in the Schrödinger picture. So the main conceptual object is the wave function So the wave function in quantum mechanics defines a pure state and the probabilistic physical meaning of the wave function is that it's absolute squared times the dx. So this is the probabilistic measure on the configuration space, and let's just for simplicity consider the quantum mechanics in RD. So this is the probability to find the point particle in U in RD, and that's the integral over U. At time t. Now, it's a physical theory, so in any physical theory we observe something. And so the whole idea of any physical theory is to describe the physical observations. So in this model of reality, in this theory, observables are Hermitian differential operators on L2 RD. And if A is such an operator, its expectation value in a pure state corresponding to psi, and I can suppress time dependence if I'm considering static situation, if I don't consider the dynamics. It's just so psi is the following. There are many ways to denote it, so this is one way. Psi complex conjugate to x, a psi x dx. A is Hermitian, so this is a real number, and roughly speaking, this is what you observe in quantum mechanical experiments. So the evolution of states, the time evolution of states, it is given by the Schrödinger equation. And it's IH d psi dt is equal to minus h squared over 2m, the Laplacian x and t, it acts on x variables plus d of x psi xt. And this differential operator is called the Hamiltonian, and I'll put check there to distinguish this Hamiltonian from the classical Hamiltonian function that we had before. So formally, and usually, so this is the equation, and then normally you set some initial condition, the wave function at time 0, and then the solutions to the solution to this differential equation is the evolution of the wave function. So formally, C x t is e to the minus I h t over h phi x. You see, it's a linear differential operator, and that's the simple equation for the vector in the infinite dimensional vector space. You can write it in terms of the, so this is a linear operator in L2, so you can write it as the integral operator with the kernel u x prime phi x prime gx prime ut, and I will switch from x to q, ut q prime, just to make it parallel to the discussion of classical mechanics. This R d is exactly the configuration space that we had in Lagrangian classical mechanics. So this is the propagator. In quantum mechanics, it has the same name as the propagator in Feynman diagrams, but and there is some reason for this. These are different objects. So from this differential equation, you can define this propagator as the solution to the following boundary problem: d dt q prime is equal to the quantum Hamiltonian acting on q, and then the initial condition as t goes to plus 0, this kernel converges as a distribution to the delta distribution diagonal q minus q prime. So the limit is equal to this, and the limit is in the sense of distributions. So in other words, you have to choose two test functions, and you have to integrate this against test functions, and this is the weak convergence on test functions. Okay, so now let's look at the property of this propagator. So this is the main hero in this discussion. Well, this is really the main gadget in quantum mechanics with the given Hamiltonian. It describes the evolution in quantum mechanics. Now let's look at its properties. First, if you take ut, take the convolution of integral operators with us, this is the same as multiplying two exponents e to the hs times e to the ht. So this gives s plus t. And second, ut is an operator in Rd, L2 Rd. So you can think of ut as a vector in the completion of the tensor square of L2 on Rd. And, well, so this is a one-dimensional quantum field theory, with the space-time being one-dimensional Riemannian manifolds, which are intervals in R. So to a point, we assign the vector space L2 Rd, and then to an interval T1, T2, we assign the vector Z T1, T2. In the completion, well, you see now it's an infinite dimensional situation, so we have to make a completion. In the finite dimensional case, it would be just the tensor product. And this Z is simply U T2 minus T1. So we constructed this gadget to a point we assign a vector space, to an interval, a vector in the tensor product of vector spaces. And this partition function has a very simple physical meaning. It's the integral kernel of the propagator for the Schrödinger equation. Something very basic in quantum mechanics. So it just shows that these axioms, it's a second illustration of the fact that these axioms is not something completely artificial. It's just maybe some repackaging of very conventional things in quantum mechanics and statistical mechanics. So,
Time for coffee, maybe?
oh yeah. So.